kick off. Good morning, everyone. Welcome to the Net Zero Technology Centre's Tech20. My name is Martin Tulloch. I'm the Head of Energy System Integration here at the Net Zero Technology Centre and your host for today. Absolutely delighted to have you join us on the webinar. Before we kick off the presentation, we've got a couple of housekeeping points to cover. We call these Tech20 sessions because we split them into 20-minute blocks. I wonder if we can pop on to the next slide, Jamie. We've got 20 minutes for our speaker today, 20 minutes for Q&A, and then finally 20 minutes for networking. So anybody who wants to stay on at the end of the call, we can promote you to a participant and have a bit of chat at the end. So please feel free to stay to that if you can. We've got two options for Q&A. We've got a Q&A function at the bottom, so feel free to add questions as the presentation is going on, and also feel free to raise your hand at the end of the session. We'll try and cover as many of questions as we can in the 20 minutes. I'd like to introduce the speaker for today, Jamie McCallum. Jamie is a senior engineer at Wood. He also, we're absolutely delighted to have him as part of the team in the Technology Centre on secondment 3 days a week. He's been an absolutely fantastic addition to the team, and he's been the lead author on this piece of work that we've undertaken on behalf of the Offshore Wind Innovation Hub, looking at floating wind, green hydrogen supply chain opportunities. I'll just hand over to you, Jamie, and give you 20 minutes to present, and look forward to some Q&A at the back end.
Right. Thanks, Martin. Good morning, everybody. Thanks for taking the time to dial into today's Tech20. As Martin said, my name is Jamie McCallum. I'm a project engineer at the Net Zero Technology Centre, a role that I'm undertaking as a secondee from my primary employer, Wood, where my background is subsea engineering. At the Net Zero Technology Centre, I'm supporting projects on our energy system integration roadmap, one of the themes of which is hydrogen and other clean fuels. This morning, I'm going to give you an overview of a study I've completed for the Offshore Wind Innovation Hub on floating offshore wind-powered green hydrogen. The study has a particular focus on the impact that projects of this nature could have on the UK supply chain and those of key regions for floating offshore wind in the UK. The study we've undertaken builds on previous work released by the Net Zero Technology Centre in partnership with the Offshore Renewable Energy Catapult on an integrated energy vision for 2050. This set a clear vision for a net zero energy system in the UK North Sea, building on our current offshore oil and gas and offshore wind resources, and integrating new technologies, including floating offshore wind, hydrogen production, and carbon capture, utilisation and storage, to deliver improved efficiency and carbon footprint reduction in existing oil and gas operations. The integrated energy vision considered 3 potential scenarios for the UK offshore energy system in 2050. These were termed emerging, progressive, and transformational. For this study, I've considered 2 of these scenarios, those within which green hydrogen production is predicted to play a major role in the UK energy system. In the progressive scenario, 75 terawatt hours of green hydrogen is forecast, which represents around 5% of the total energy mix. This is supported by increased offshore wind deployment beyond the targets set by the Committee for Climate Change in 2019. And a good proportion of this deployment would be required to be floating to meet this deployment forecast. In the transformational scenario, green hydrogen plays an even bigger role. 253 terawatt hours of green hydrogen is forecast, representing around 16% of the total energy mix. This requires even more offshore wind deployment, double the target set by the Committee for Climate Change in 2019, of which at least half would be required to be floating. So in terms of the scope of this study, consideration is given only to UK-based floating offshore wind-powered green hydrogen. And to ensure that production is 100% green, I've made an assumption that power is coming only from a dedicated floating offshore wind facility with no backup supply from the grid. Our modelling also only considers upstream production costs and not other costs associated with midstream and downstream delivery. We've considered 3 separate pricing scenarios. The first with equipment costed at present day prices, and we've then applied 2 cost reduction profiles. The first profile reduces the cost of the floating offshore wind to a comparable levelised cost of electricity with current contracts for different strike prices for fixed bottom offshore wind. This is currently around £40 per megawatt hours in 2012 prices. The second reduces the cost of the green hydrogen production equipment, such that the levelised cost of the green hydrogen is equivalent to UK government projections for 2050. These were released alongside the government's white paper for hydrogen and is around £70 per megawatt hours for green hydrogen production from a dedicated offshore renewable source. We've also considered 4 separate project case studies. These were developed with key regions for floating offshore wind in the UK in mind. These regions being the north and east of Scotland, northeast England, and the Celtic Sea. Each case study considers a different method of combining floating offshore wind power and green hydrogen production with additional complexity in each. Our first scenario considers a floating offshore wind farm located close to shore. Power would be exported to shore to an onshore hydrogen production facility. This scenario would be particularly suited to somewhere like the Shetland Islands, where the offshore bathymetry and wind resource is such that floating offshore wind close to shore is viable, as well as having existing infrastructure which lends itself to the onshore production of hydrogen gas and transportation directly into the national transmission system. The second scenario considers a floating offshore wind farm located far from shore, in an area where there are offshore oil and gas facilities approaching cessation of production. These could then be repurposed as hydrogen production facilities, as well as making use of existing export pipelines to shore. This scenario would be particularly suited again to the Shetland Islands and also to the northeast of Scotland more widely, given the location of the Sullom Voe and Sage terminals and offshore oil and gas facilities in the northern and central North Sea exporting to those terminals currently. The third scenario is a replica of our second scenario, but with offshore hydrogen production facilities and export pipelines being new builds in this instance. This brings into play regions such as the northeast of England and the Celtic Sea, where onshore reception facilities exist, but where there is a lack of offshore infrastructure to repurpose. And finally, the fourth scenario looks at a different export option. The export pipeline in this case study is replaced by export tankers, offloading produced hydrogen from storage tankers periodically for transport to UK or international markets. For each case study and pricing scenario, models to calculate both levelised cost of electricity and levelised cost of hydrogen have been developed. From the levelised cost of hydrogen models, spending breakdowns are output, providing the levels of spend on each system component for viable projects. These spending breakdowns are used to calculate numbers of jobs created in each spending area, using the same methodology as that in the Integrated Energy Vision project completed by the Technology Centre and the Offshore Renewable Energy Catapult. Calculated job numbers are combined with an assessment of local supply chain job retention in each region and the UK national supply chain for both floating offshore wind and green hydrogen production. The assessment applies multipliers to the numbers of jobs created by project spend to estimate the numbers of jobs that could be expected to be retained within the UK supply chain on a floating offshore wind-powered green hydrogen project. I'll now move on to the key findings from the study and provide an overview of each. Based on the progressive and transformational scenarios of 75 and 253 terawatt hours of green hydrogen production, respectively, meeting these scenarios would require 9 and 31 gigawatts of floating wind capacity to be producing green hydrogen in 2050, respectively. This assumes that 50% of the electricity requirements for green hydrogen production in the UK are being met by floating offshore wind, reflective of an increase in floating offshore wind in the UK's energy mix as nearshore fixed bottom opportunities become fully utilised. Average present value life cycle spending on one of our gigawatt scale case study projects considered herein is circa £5.5 billion. Thus, total life cycle spending across the number of projects required is between 49 and 170 billion pounds, depending on the deployment scenario to be met. To meet the UK government's 60% local target, therefore represents an opportunity of up to 68 billion pounds for the UK supply chain in the case of the transformational scenario. And the main driver of the levelized cost of hydrogen is the cost of electricity, i.e. the levelized cost of electricity of the dedicated floating offshore wind farm in our case studies. The figure on the top right presents the proportion of hydrogen cost contributed by the electricity cost of offshore total wind expenditure compared with green hydrogen capital expenditure, operating expenditure, and decommissioning expenditure. The example presented is for our first case study, where green hydrogen is produced onshore. This is the lowest case study in terms of levelized cost of hydrogen. Costs are representative of present day pricing, and electricity is responsible for 72% of hydrogen costs in this example, which represents a levelized cost of electricity of £91 per megawatt hour. And the figure on the left of the screen presents this pounds per megawatt hour in terms of the cost of hydrogen rather than simply as a percentage. Reducing the levelized cost of electricity to £40 per megawatt hour in parity with current strike prices for fixed bottom offshore wind can reduce the associated hydrogen cost by almost 60%. This level of cost reduction would require a 51% reduction in offshore wind costs and associated improvement in electrical losses, raising net capacity factors. Alternative solutions could come in the form of increased turbine capacities, improved gross capacity factors, or deployment of alternative turbine technologies to improve overall wind farm yield. Even after reductions of this level, electricity is still responsible for over half of the cost of hydrogen, as shown in the figure on the bottom right. And electricity costs may need to fall further still below the current strike price of fixed bottom offshore wind to make floating offshore wind powered green hydrogen projects viable. So significant cost reductions and technological improvements are required to make green hydrogen production from floating offshore wind. Modelling of hydrogen costs at present day prices estimates green hydrogen produced from floating offshore wind to cost between £6.81 and £8.63 per kilogram. To provide a comparison, this represents a significant uplift on UK government projected costs of green hydrogen from all offshore wind, including cheaper fixed bottom offshore wind power for 2025 of between £3.64 and £3.87 per kilogram. Cost modelling is repeated, with cost reduction profiles applied across all areas of spending to reduce both electrical and hydrogen costs to £40 per megawatt hour and £70 per megawatt hour respectively. This requires cost reductions of 51% for floating offshore wind and between 52 and 72% for green hydrogen production, depending on the complexity of the project considered. Reductions of this scale represent a significant challenge to UK industry and indicate that substantial investment in finding new disruptive technologies is required. However, this is a challenge that the UK supply chain has risen to before. Comparing the predicted cost reductions required with the profile of reductions in contracts for different awards in fixed bottom offshore wind developments to date, we can see that the reduction rates required are similar. Reduction rate predictions modelled here for floating offshore wind are based on Offshore Renewable Energy Catapult projections for various innovation and deployment scenarios. And it's worth noting that these were released prior to the ScotWind Awards and were based on between 8 and 16 gigawatts of floating wind deployment. ScotWind Awards alone amount to just under 15 gigawatts of floating wind deployment. Reduction rates for green hydrogen are based on the modelled scenarios in our study, with levelised costs rated to 2012 prices for comparison with the contracts for difference award prices. Our final finding is that the UK supply chain will require investment in high spend areas to meet 60% local targets. The UK would fail to meet the government's target of 60% UK content in the sample floating offshore wind projects considered in our study without investment in the supply chain. The table on the left provides a summary of the improvements in job retention levels in each spending category required to meet the 60% target for both TOTEX and CAPEX. These are split because the largest proportion of project spend is on operations and maintenance, as this tends to be heavily localized by its nature. However, public discourse around job creation tends to be focused on capital spend and manufacturing of critical components. To reach 60% UK content, a high level of operations and maintenance jobs will need to be secured locally, and steps taken to improve UK supply chain competitiveness in CAPEX areas with high proportions of jobs retained within the UK supply chain. The highest proportion of floating offshore wind CAPEX is created by spending on the wind turbine. This is an area currently dominated by incumbent OEMs whose operations are based mainly overseas. Increasing levels of jobs created in this area in the UK will therefore require making the UK an attractive location for these OEMs to create manufacturing bases, or disruptive technologies from UK SMEs invested in to provide alternative, cost-competitive solutions. A further 22% of CAPEX jobs are created in the procurement and manufacture of the floating substructure, this being the second highest CAPEX spend area. Thus, designs which can be fabricated locally at UK ports need to be harnessed. The UK is projected to meet its local content targets for green hydrogen production. This is driven by the fact that an even larger proportion of jobs created by spending on green hydrogen production is in operations and maintenance. Thus, once more, the levels of job creation required for both 60% of total expenditure and capital expenditure are presented here. The table on the right presents a summary of these requirements for green hydrogen production. CAPEX job creation is mainly driven by electrolyser spend. This represents over half of CAPEX-related jobs in all case studies. SMEs developing electrolyser technologies therefore need to be supported to create and develop manufacturing bases in the UK, anchoring this critical infrastructure for both local projects and export opportunities. The other area of significant CAPEX job creation is in hydrogen compression systems, and increasing UK content in this area would be required to meet 60% content targets for capital expenditure. And on that, to close, I'd like to thank our Energy Transition Alliance partners, the Offshore Renewable Energy Catapult, for their support in developing the supply chain job modelling calculations. I'd like to thank Exodus for providing the basis of our levelised cost modelling, and my colleagues at Wood for their assistance in developing the case studies considered. And finally, thank you all once again for taking the time to sign into the call today. I look forward to your questions.
Fantastic. Thank you very much, Jamie. That was absolutely bang on time, just I think 1 minute under 20. Really insightful presentation. We are going to publish the report within the next week, hopefully. We're just putting the finishing touches to that. So we'll send you an email with a link to that as soon as it's ready to be published. Everybody who's attended here, and of course it'll be on our website. But really keen just to get some Q&A and some discussion. So if anybody's got any questions, any comments, any thoughts, please feel free to put up your hand or type them into the Q&A box. But really keen to try and make this interactive if we can. Are there any burning questions from anyone? Let's see if I see a hand going up there. It's down. I'll maybe kick off, Jamie, just with a question on the sort of international competition in this space. You mentioned the real need to drive down the cost of electricity, because I guess this is a global competition to deliver green hydrogen to where the demand is going to be. Have you got any thoughts on who the main international competitors will be?
So in terms of who the competitors will be, the main focus tends to be on Chile, Qatar and other countries in the Middle East, and also Australia, countries that have access to large-scale solar PV, just because it has the lowest levelized cost of electricity. And as I've said, that's the main focus for driving down the cost of green hydrogen. One other thing that was interesting coming out of the study is that we looked at the cost associated with using export tanker offload rather than building new build pipelines. Now, for our study, that was just considering export offload to shore somewhere in the UK. So we only really considered the upstream cost impacts, but we found those to be significant. So if you add those cost impacts with the conversion of hydrogen into an appropriate carrier, plus the transportation costs in midstream and getting green hydrogen to the UK, I think there's some work to be done there to see what level the upstream cost actually needs to come down to in the UK before it is cost competitive with other countries that are in other parts of the world and have significant transportation burdens.
Yeah.
Not to mention the potential carbon impacts that may have also.
Absolutely, thanks for that. Got a couple of questions coming through the Q&A. I wonder if people want to ask them themselves. I think it always makes it a bit more interactive. Let me see if I can give you permission. Shruti, do you want to ask your question live?
Yeah. Hi, Jamie. I wanted to ask that recently, or I think February 16, DMV launched, started a JIP for the electrolyzer. Do you think that's going to help significantly reduce and bring down the cost of electrolyzers and green hydrogen production?
I mean, any cross-industry collaboration will only help. And yeah, in terms of impact on the cost of hydrogen, making the electrolyzers more efficient and also improving their degradation over life are two critical aspects of that levelized cost of hydrogen, which would need to be improved to meet the targets that we're seeing.
Okay, thank you.
Do you have any personal involvement in that DMV JIP?
No, I don't. I was just reading online and that caught my attention.
Yeah, it looks like a really interesting concept, cross-industry project, and I believe it's open to new partners joining in the next few months.
They have it till April, so they have big names like BP and all in it. So it would be great to see how that's going to help reduce, move the focus more to green rather than blue hydrogen?
Absolutely, yeah, there's so many common challenges there. It's great to see that cross-sector approach, and it's exactly the same type of approach that we promote here in the Net Zero Technology Centre. I see another question from Irina. Do you want to come on and ask that one, Irina?
Yeah, sure. Thanks, Martin. Thanks, Jamie, for that presentation. I was wondering if you could say a little bit more about what kinds of government support would be most appreciated by companies. You mentioned, obviously, support for electrolyzers, but do you mean things such as funding, or is it more regulation, or is it coordination groups? Just to get your thoughts.
I mean, funding will be the number one, and creating suitable incubators and supporting cross-industry bodies to keep those companies located in the UK, but also backing demonstrator projects, because they have to have a foresight of projects to aim for in order to start developing things like large-scale manufacturing facilities. If I look at offshore wind as an example, if we wanted a turbine manufacturer to commit to building a plant in the UK, they need foresight of large-scale deployment in the UK, and hopefully things like Scotland, and when those projects start to move down the development timeline, things like that are sufficient to encourage the establishment of large-scale manufacturing bases here.
Patrick, do you want to come on? Let me just promote you to a speaker here.
Yeah, great. Thanks. Great presentation. Thank you very much. I guess I was just wondering, we're sort of having an outlook there to the levelized cost out to sort of 2050. I'm wondering what sort of technology improvements or advances you've assumed there that might take place in those ensuing decades that may then, lead to, or built into those costs you've given, or maybe even accelerate those costs further down?
So the scope of our study didn't consider what specific technological advances would be required to meet those cost reduction profiles. What we did was looked at the government target for, or the government projections that came out with the UK Hydrogen White Paper, which effectively provided an end value that industry is looking to get to, and used a back calculation to work out how much reduction would be required. Perhaps a suitable next step, a follow-on step for the study would be to investigate specifically what technologies are out there and being developed that could contribute to that reduction, and what impact each would have, in order to prioritise government funding in the right areas.
Yeah, I'll maybe just add to that. We have got a technology investment roadmap at the Net Zero Technology Centre that focuses on green and blue hydrogen cost reduction. So in that, we're targeting everything from reducing the cost of desalination to reducing the cost of existing electrolysis techniques, but also with a focus on potentially disruptive technologies. But as Jamie said, that wasn't part of the scope for this piece of work, but it's definitely something that I think deserves more attention and a structured approach. And things like the DMV JIP is exactly that type of approach that we need as an industry to adopt. Any more questions? Colin, I'll give you speaking rights here, and it'd be great if you could ask your question. There we go.
Yes, a great presentation and a great overview, and that's what's really been missing. I've seen the direction of travel, so and I appreciate a lot of great technologies being discussed and brought through the NZTC. We've been looking at what existing technology is out there, and one particular UK company who we're trying to bring onto the technology platform said they were so busy, they had so much activity, that they didn't want to showcase it because the hydrogen market was so busy for them at the moment. And I just wondered if we'd done a mapping exercise to see who the players are and if there was then a collaboration opportunity and inward investment for Scottish and UK companies to then work with them who maybe are international at the moment.
So such a mapping exercise was something I looked to find at the start of this study, such that I could understand the nature of the UK hydrogen supply chain. There has been some work performed by Exodus for the Scottish Government on the Scottish supply chain specifically, which is available publicly on the Scottish Government website. And I spoke with the Energy Systems Catapult, who had done a similar exercise for the hydrogen supply chain, but specifically related to like heavy goods transport. But I think that that UK-wide piece of supply chain mapping and what that looks like in the hydrogen industry does not exist as far as I'm aware. And I agree would be a useful exercise to be performed.
Yeah, because I mean, on NZTC obviously do this a lot of look. There's no point in developing a new technology if something already exists, and just to make something another competitor in market, you're always looking for game changing. But I also feel that there's a huge opportunity for Scottish UK companies to partner with others, because when you show that map, the market potential is enormous. So. But you need that anchor in the, let's say, northeast of Scotland. Obviously, I'm parochial about that, but certainly in the UK. So I do see there's a big opportunity to work with international companies and bring them to the UK.
Absolutely, Colin. I totally agree with them. I think you know the market better than anyone, and there's huge opportunity out there. I guess one thing I will add that we work quite closely with Offshore Energy UK, and they're undertaking a supply chain mapping exercise at the moment as part of the North Sea transition deal. So that will hopefully give us some more data and market opportunity. We are looking at a technology study as a complementary exercise. Again, that will be published hopefully April, May this year. It's ongoing at the moment. I noticed Murray Bainbridge from Scottish Development International's on. I don't know, Murray, if you want to come on and add anything in terms of the international opportunity, both for export and potential partnering with for Scottish companies.
Hello, Martin, can you hear me?
Yeah, loud and clear.
Yeah, I mean, Jamie mentioned those sort of competitor markets, and they kind of tie in quite nicely with markets that we see as potential partners for our supply chain as we develop capability here in Scotland. Not all of them will be related to offshore wind, and as Jamie has highlighted already, some of these markets like North Africa, Middle East will be looking to use their solar potential in delivering green hydrogen in particular. So we do see markets overseas as providing opportunity, particularly where there may be elements of blue hydrogen as well, in markets like the Middle East, but definitely echo what Jamie said around markets like Chile, Middle East, North Africa, Australia, where we see opportunities for our supply chain companies and technology companies to play a role in helping those develop and deliver their green hydrogen ambitions.
No, I'll say brilliant. Thanks, Murray, and sorry for putting you on the spot there, but I think the team at SDI have got a really crucial role to play in the energy transition. It's absolutely brilliant to see what you've done so far, and I think we just need to make sure that more people are aware of the good work that you're doing.
Yeah, we certainly welcome any engagement from any companies that are considering taking their technology or their capability into overseas markets. We stand ready to try and help them do that.
I see a really good question in here from Glenn McCallum. It's a subject that's pretty close to my heart, with the skills challenge and the skills opportunity as well. I wonder if you want to come on, Glenn, and just ask the question personally.
Yeah, thanks, Martin. It's just something that comes up time and time again when I'm speaking to, like, I'm based up in Orkney, obviously, as you can, but the supply chain thing is a massive issue for all of the developers that are coming here. I mean, we're speaking to loads of them, and I just wonder if the targets that we've got, the deployment targets that are being bandied about, and are they realistic given the amount of supply chain issues that we're going to have on, like, even just basic the turbine manufacturing, and I understand that the amount of anchor chain that is going to have to be fabricated in the coming years it's mind blowing, and not to mention having the fabrication facilities to be able to build the floating wind structures and that's kind of thing. And then there's a huge requirement for skills that, so I can't even remember who it was that told me the number of welders that was going to be required just to actually handle the basic putting together of the floating structures and that type of thing. So I just wonder how realistic our targets are and how far they're going to stretch out if we don't get this sorted.
Hugely important question. I don't know if you got any thoughts on that, Jamie. Did you look at job numbers and specific disciplines as part of the work?
Not in specific disciplines, no. It is worth noting that if you look back at the targets that had been set to date for offshore wind, the UK hasn't met any of them, as far as I'm aware. If you look back at what was initially projected for 2010, 2015, 2020, it's always good to set ambitious targets, but I agree, I see that as the number one issue with Scotland and also INTOG coming up is the sheer scale of deployment. And it's a different type of deployment to what we're used to seeing in oil and gas, which is build one and build big. This is the serial deployment of many units, and it's going to be interesting to see how the UK supply chain can be set up for that.
Can I ask another kind of slightly different question, Martin? It's not on hydrogen, but it's on Scotland, and it's the 25 gigawatts of floating wind around Scotland, most of it around the north of Scotland, and the challenges that we have in Scotland with the grid. So not all of those fields are going to be able to tie into something that's going to create hydrogen. So there's going to be a lot of it needs to get into the grid one way or another. And I think I heard that the north of Dundee, the grid is very flaky in Scotland. So what is going to come to pass with that? Any ideas?
Really good question. Jamie, do you have any thoughts? I can come in after you.
Not specifically. I know from speaking to our putting my wood hat on here, we have a power and transmission onshore service line, and I spoke to them on some of the cost numbers that are being assumed for onshore integration to grid and onshore substation construction, and they were highly skeptical of the numbers that are out there as estimates, because those estimates are based on fixed bottom wind farms that have been built to date and had plenty of capacity to tie into the grid, and so didn't have to deal with this problem that we're going to have coming up with Scotland, where you have huge deployment numbers all in a fairly similar area in terms of the grid, and significant investment required to make sure that the grid's up to scratch, and that will almost certainly have to be passed on to developers of the wind farms.
I think Scotland's just highlighting an issue that I guess, Glenn, people like you and I have known about for well over a decade, just the great resource that's to the north of the country, and all the demand is down at the other end, and the grid system is not really designed to accommodate that sort of resource and demand profile. And I guess the ballpark figures that I've heard people talk about is roughly 5 gigawatts of capacity on the grid for that 25 gigawatts of Scotland licenses. So absolutely, if the cost of floating wind can be reduced significantly, hydrogen could be an option. We look at the likes of Port of Rotterdam, they want to import 3 times Netherlands' annual energy demand through Rotterdam, and feed a lot of that into continental Europe, where there is a lot of industrial demand in particular. So it's going to be absolutely fascinating to see what happens. It's from a technology perspective, yeah, there's certain things we can do. We're focusing on reducing the cost and the scale of things like HVDC converter stations, but that only goes so far. I think it's that the policy and the regulatory aspects that are absolutely crucial to tackle here. Again, that's out with the scope of this study, but something that's going to be really important. I see another question come in. Do you want to ask that one, Shruti?
Yes. Yeah, I don't work fully in it, so it's only things that I've read online, and I was seeing that there's 40 something designs for offshore wind. And now that we are talking about the supply chain, because if you had to manufacture it and each design is different, like would you think that's going to be a problem, or that's going to stop the scaling of the technology?
I think the 40 number might actually be low. There's a ridiculous number of different designs out there, but what the scale of deployment I think will mean is that the designs that we see being deployed first might not necessarily be those which are deployed en masse, because deploying a few demonstrator units is not the same as having to serially deploy locally manufactured substructures in their hundreds. So both in terms of the material used and the size and scope of the designs, I think we'll see different designs winning the day when it comes to the actual deployment of Scotland.
Because the other thing was the ports that we have as well, like the draft restrictions, and that is also something that has to be sorted out to have more local supply.
Yes, so I mean, there's 10 or 11 floating wind turbines off the UK at the moment, and none of the substructures were fabricated in the UK.
You're missing out on that. Thanks.
Okay, well, thank you very much for that last question. We've just gone over our 20 minutes of Q&A. Let's say a big thank you to Jamie for presenting today. A huge thank you to everybody for attending and for staying for the Q&A. Thanks for making it so interactive. Hopefully we'll be able to do this sort of thing in person and in hybrid form sometime soon. Thank you very much. Have a great weekend, and feel free to get in touch if this presentation has sparked any ideas or opportunities that you'd like to discuss with us as a technology centre. We're always open to working in partnership on the huge challenge that lies ahead here. So thank you, everyone.